Hello. So today we're going to be talking about shifting lines, and ultimately what this is going to be talking about is like the first video in a series of essentially understanding what we call function transformations. Now, of course, we're talking about shifting lines here, and I'll go ahead and remind that lines are essentially of the form f of x is equal to mx plus b, where we have some input, x, and some output, f of x, with a couple of things that can impact the inputs that you plug in, such as what we call m, which is the slope of your line, and the y-intercept. Now, in a previous video, which I've yet to create, I'll talk about function notation generally, speaking a little bit more in depth. And as a summary from what I'm going to do, you will have the following. If I have a function that, for instance, is like f of x is equal to, say, 2x plus 3, if I were to plug in a number, so let's say, okay, so input, output. Currently my input is x, my output is f of x. If I wanted to put the input, so let's say we make a table here, inputs, let's say, and outputs. If I want to plug in the number 6, or heck, let's use 2, probably a smaller number. If I want to put the number 2 in, what I'd write is f of 2. Now, in terms of my actual equation here, I would have my function evaluated at 2, f of 2, my function of x at 2 is equal to, well, where I see x, I'm going to plug in 2 times 2 plus 3. Now, if I went ahead and just plugged along here, I would get 4 plus 3 equals 7. But I really only care about this result there. Because next thing I'm going to start plugging in is not going to be a number that we can crunch the numbers for and actually come up with a nice crisp result like the number 7 there. What I'm going to plug in next is the letter t. Oh, let me go back to my pen, the letter t. So if I plug in t, the output should be f of t, my function evaluated when you have an input of t. Now t, just like x, is just a variable. It doesn't have a specific value, or at least not one that we know of. And we kind of assume that it's like any random number. But I'm just kind of writing a different representation for it. And the reason I'm doing this right now is to show that the process for plugging in non-numbers is essentially the same. Wherever you see x, you're going to put what you have as your input. So in this case, it would be f of t, the function evaluated at t, is going to be equal to 2 times t plus 3. Cool. Now, let's start having a little bit more fun with this. One thing we can do is I'm going to extend this table a little bit, and mind that I'm switching to pink here. I'm going to change my input to be 2t. Well, go ahead and guess what the result's going to be. The output should be f of 2t. Because I take what I'm inputting and plop it in that spot for function notation where you put your inputs. And the output is, of course, just read f of 2t. This guy will give you f of 2t is equal to, well, here's the x. Here's where I plug in my inputs. I'll get 2 times, in this case, 2t plus 3. Now, if you wanted to, you could go ahead and say this is 4t plus 3. But right now, I don't care about that yet. What I care about is just looking at this representation. Notice what I do. I plug in that expression. And notice this expression here is the input being multiplied by 2. So here's t. Here I am now multiplying the input by 2. And the reason I'm making this so explicit is we're going to talk about this here in a bit. Now let's say we go ahead and do something else as well, because we could multiply an input by a certain number. And I'm going to switch from t back to just x. Imagine I took my input and I said, I'm now going to input x plus 2. So instead of plugging in x, I'm going to plug in x plus 2. Now, like for instance, if x was 1, that would be 0 plus 2, which is just 2. So in essence, I'm plugging in the number 2, or rather, I'm plugging in 2 more than I technically, quote unquote, plug in initially. Now, in terms of representation, think about what this is going to look like. It's going to be f of x plus 2, close parentheses. And how are we going to plug this in? Well, the same exact way. We'll have 2 times x plus 2, and then of course the plus 3. The overall structure of your equation is the same each way. You get 2 plus 3, and then you multiply the 2 with your input. And again, I could distribute that 2 in this case to the x and the 2, and then combine like terms. However, just looking at this, the structure is the same. And that's kind of what I want to get across here. This idea, if I can modify my input, it's the structure of your function is still the same. You're still doing the same things. The function of it in of itself doesn't change in that sense. What you are doing by plugging in something like this, x plus 2 or 2t or just t, or plugging in 2, is you're changing what you're plugging into the function. You're not changing the function. Ultimately you're going to change the graph, the outputs, and technically you're modifying the inputs, but the function itself is still f of x is equal to 2x plus 3. Now, let's go ahead and experiment a bit. So, let's make two tables. One is going to be f of x is equal to x. Well, okay, sorry about that. We're going to now consider an equation. So this one is just going to be f of x is equal to x. And we're going to go ahead and see. We're going to make a chart, little t-chart again. But here, I'm just going to write, in general, the input and the output here. Now I'm going to let's start with this one, this x plus 2. Because this is going to talk about like vertical, so up and down or left and right movements of my graph, which I'll also, actually let's go ahead and start with that. I'm going to go ahead and draw a graph. I'll go ahead and talk about this first so we can kind of link back to it in a second. I could initially draw a curve. This is going to be that function right there, f of x equals x. You can imagine I take this function and I could move it around on the plane. I could move it up, down, left, and right. I can move it a combination of both of them, but ultimately, I'm just going to shift it around. Another cool note is that if I move it up, or if I move it left a certain amount, in both of those cases, my line's going to look the same. So for instance, if I were to draw a new line right here, for instance, this pink line, I could take my white line, so it initially starts here, I move it up, eventually it's going to match up. And if I move it left, eventually it's going to match up. Now you might notice, of course, like the tip of my arrow right there, at first it's going to go way up north, and subsequently it's going to go west or left. While the line that you produce is the same, the manner in which you produce it, where the points came from and where they go, changes. And this is what we're going to explore in this example here. How to move your graph using the equations, because the equations are very powerful and it lets you not have to draw out the graph every time and try to represent it. Although you always can if you want to check like your understanding of what you're actually doing. And it's always fun to mess with equations too. But let's go ahead and play around with the situation. So first of all, my function. Let's go ahead and plug in the numbers 0, 1, 2, 3, 4, and 5. Now, why am I doing all 5 or 6 numbers here? Just give myself a little bit more to work with. Let's go ahead and do this. So, if I take my equation and I have input of x and my function f of x, the outputs, is equal to, well, basically it says output is equal to input, then of course my outputs should all be equivalent. I should get 0, 1, 2, 3, 4, and 5. I'm going to erase those real quick. Now, up here, notice I changed the input in this last example to be x plus 2. So let's go ahead and make a new table where on the input side, I write x plus 2. And the output side, I'm going to write, well, just what I did before, f of x plus 2. However, now let's actually plug numbers in. And let's go ahead and make it in line, so side by side with the previous graph. So let's actually imagine I'm plugging the same x value in at the same time. Let's see what happens. Well, we get 0, so 0, plug it in, 0 plus 2, I should get 2. And then same thing, we get 3. When we plug in 1, we get 1 plus 2 is 3. 2 plus 2 is 4. 5, 6, 7. Now, if my input is x plus 2, my output is f of x plus 2. And remember, the function initially was this guy. We're still using the same function. We're just changing what we plug into it. Well, the input and the output should be the same. So I'm going to get 2, 3, 4, 5, 6, and 7. Notice if you look at each one individually, you still get the same relationship. The input is equal to the output because the base function that we're trying to transform in here, the function is still the same. We're just changing what we're plugging into it. Here I'm like essentially plugging the numbers in that are 2 greater than the quote unquote input, like the original input, so to speak. All right, so what does this mean? Well, this is where it's helpful to, at least initially, reference the graph. So I'm going to zoom out a little bit. Down in white, I have this function already placed on the graph. If you want to, I can map the points, 0, 0. Imagine this is 1, 1, 2, 2, 3, 4, and 5. Let's make the line go all the way through, because I have the luxury of doing so. Well, let's go ahead and see. Let's go ahead and play around a little bit. Let's see. I'm actually... Well, let's go ahead. Okay. I'm going to go ahead and just plug in the points for this line now. This line, when x was 0, I ultimately got an x, or an output of 2. So 0, 2. When the input was initially 1, and when I plugged it into my modification of the input here, I got 3. So 1, 3 should be right here. And the same thing, as we move forward, we should get 2, 4, and so on and so forth. And we produce this line. Now, what I'm going to notice is the outputs. When I plug the number 2 in to my initial equation in white, I'm actually going to circle it in white as well. When I plug the number 2 in, I got an output of 2. So I plugged in the number 2, and I got an output of 2. When I plugged in the number 0 to the other equation, my function, based on my modification of the input, essentially treated that 0 as though it was 2 and spat out the number 2 as a result. And the way I like to think about this is that this number 2, this function, f of x plus 2, takes these x values. And I'll go ahead and put equals x plus 2 in this case, where like the input and output are the same. It takes these values, these x values, and if you plug them in, the extra plus 2 right here makes the output act as though it's the output from the original graph. So I'll look at 0 and I'll look at 2. If you plug in 0 to this equation, you get an output of 0. Actually, hang on, backwards. I wanted to say, if you plug in 2, mind me, if you plugged in the number 2 to this equation, you get an output of 2. So you get f of 2 equals 2. You get this point right here. If you plug in, for instance, 0 to this equation, I'm going to go ahead and erase those two lines right there. What you get is f of 0 plus 2 equals 0 plus 2, which if you were to simplify both of these two things, you get f of 2 equals 2. And so when you plug in the number 0, what I like to think about, this equation, when you add 2, makes that 0 look as though it is the number 2. The output 2 here, if you plug in 2, you get 2 out. If you plug in 0 to this equation, it acts like 2. And in that sense, or at least I like to think of, it shifts your curve, your line in this case, over to the left. It makes points that you plug in, the inputs, act like the points, the inputs that are 2, I guess, inputs greater than what you actually plug in. Because here you essentially take the number 0, plop it in, and it acts like 2 as the input of the other function. It copies it, but it also does it a little sooner. You can say it shifts left here. And from this, we have a little general statement that if you have a function and you take the inputs and you were to shift it, let's say by some number, which I'm just going to call h, what this does is it will shift your function, shift the function left by, now go ahead and write by h. So here, if h was the number 2, your function got shifted to the left by 2. So f of, if h is 2, then f of x plus 2 shifts f left by 2. Now you might ask, like, what if it was a subtraction? Well, if you subtracted, then, for instance, if you went like f of x minus 2, this negative 2 right here, when is it gonna, if I do x minus 2, when does x minus 2 equal 2? Because that's kind of what I was using as a reference here in the previous. When does x minus 2 equal 2? Well, if x is equal to 4, then of course you have 4 minus 2 equals 2. And if you were to think about it, if I were to plug that in, f of 4 minus 2 equals 4 minus 2. When I plug it in, I get f of 2 equals 2. So for this function, if I were to make it minus 2 instead, when I plug in 4, it'll act like the original function. In this case, it's going to shift to the right. And so if you see f of x minus, oh sorry, I shouldn't put the parentheses there, f of x minus 2, it should be a t right there, it's going to shift your function, shift f right by 2. And this is the counterintuitive sort of deal here where in math, you'll hear everyone say it feels counterintuitive that you have a addition sign moving you left and a subtraction sign, a minus sign, moving you to the right. But it's not that you're adding a positive number, so like you're thinking you're going in the positive direction. Rather, what your function does is the transformation acts like the same line that is moved to the right. So it's going to act like it. It's going to pull those points actually to the left. It's going to pretend like all the inputs are 2 greater than what they actually are, which makes them occur sooner, which makes them occur to the left. And with the f of x minus 2, that minus 2 means your number is going to act like the numbers that are 2 less than your point. And so it kind of pulls those points forward, so to speak, and you get this new line, which I guess I could have done in yellow, but I drew it in blue here. It acts like the points, it acts like the line that is 2 to the left of it. It acts like it, and it essentially becomes it later on towards the right. And so this general rule, if you were to look at, if I were to just say, how does f of x plus 3, without even naming a function, maybe I wrote like g of x plus 3. And maybe I don't even tell you what the function is. Maybe it's g of x equals x. Maybe it's g of x equals x plus 6. Maybe it's g of x equals 2/3 x minus 2.5. No matter what, these are, first of all, these are all lines. But even then, even if you did like functions like g of x equals x squared plus 2 or something like that, which we'll talk about later with quadratics, the same effect, what it's going to do is make your function, whatever it is, right now it happens to be lines, it's going to make it act like the same function, so g of x, which is, so like maybe I do a quadratic equation, maybe I do like a little line here, and I'll make this white so you can see it better. And I guess I can redraw that as well. If your function is this one, so maybe g of x is this curve right here, then the plus 3 here is going to make your function act like the one that is actually 3 units to the right. Oh, sorry. This is the function that's facing the eye. So your new, oh my goodness. Even sometimes it is still confusing thinking about it. Or you might get lost in your words for a second, like I did there. Rather, your new function, if you add 3 to the original one, is going to make it occur sooner. Each of the points, each of the outputs are going to occur sooner. So each of the outputs are going to occur sooner by roughly 3, or exactly 3 in this case, but by whatever number you plug in there, and that's going to make it shift to the left, because it's going to act, your new curve is going to act like the one that's 3 units to the right of it, but it's actually going to occur sooner. It's going to act like the one that's 3 to the right of it, but it occurs where it actually does to the left. And so a plus 3 moves you to the left, acting like the curve that's 3 to the right. All right. Now in the next video, I will go ahead and talk about what happens when we have this case, with a number multiplied by the input. But for now, hope this helped. And yeah.